Thank you very much, Jana. So I'm Timur, so I'm from University of Nevada, Reno, and I'm going to talk to you about, well, this is a collaborative work. This is collaborative work and collaborative interaction between my group and the GILA group, Professor Jun Zi and Anna Maria Ray, and also the group at the University of Toronto, headed by Professor Paul Brammer, and these great postdocs, Adrian DeVolder and Masato Morita. So before I start, I just want to say why I'm here today is because of the Burning Man Festival in Reno. So I just want to have a connection because I don't know if you haven't heard of it. It's really interesting. So it's like 80,000 people in the Black Rock Desert, 40 miles north of Reno, and they're like freely expressing themselves. And the interesting thing is that it's actually the nearest close place is called Gerlach, Nevada, and Samuel Goodsmith was a professor at the University of Nevada, Reno. So it means that actually Reno has very deep connection with the invention of spin. Right? So both from the theoretical side, which is Goodsmith, and then from experimental side. I must be honest, I don't know if this place is, named after the Gerlach, but I couldn't find any information online, so I'm just assuming that, it was him. So it was the Gerlach here with Otto Stern discovered the electron spin. So I have to talk about spin 1/2 systems, right? So this is qubits, right? And this is what I'm going to talk about. But before I do, I want to mention that there's a range of projects I'm working on in my group, but actually by background I'm like an theoretical AMO physicist and chemical physicist. So I spend most of my time just doing some quantum dynamics calculations on ultra-cold molecules and quantum control. So this is part of what I will be talking about today. But most of what I'll tell you about today will have to do with quantum information science, with ultra-cold molecules, and then there's some rest of the projects that I'll not talk about today, but just like they're in gray, so don't pay attention to them. First of all, I'd like to tell you about how we can utilize these vast resources or vast number of degrees of freedom that ultra-cold polar molecules provide. So this is kind of their advantage with respect to atoms. Can we work with them? So this is kind of like a typical energy level spectrum. Actually, this is a realistic Zeeman energy level spectrum of KRB molecules. So you see this, there's no shortage of levels really to choose from, right? If you have a qubit, if you want to use a qubit, there's almost more than 100 levels even in the ground. So this is the ground rotational states, and molecules like spherically symmetric. This is the first excited rotational states, and these are nuclear spin states. So there's a tiny spins in KRB molecule that are actually responding to an external field, the tiny magnets, right? And those gives rise to very small energy splittings on the range of smaller than megahertz. At small like under 100 Gauss magnetic field, and these are nuclear spin states, right? So ultra-cold molecules therefore are we think they are great for quantum information, because what you can do, for example, you can store quantum information in these nuclear spin states, right? There's this green rectangle. So the coherence time of these nuclear spin states is like tens of seconds, or can be extended even longer. So this is excellent quantum information storage medium, right? That's one thing. Another thing that actually works in favor of ultra-cold polar molecules is that there is long-range dipole interactions. If you encode your qubit in the same nuclear spin states of ground and the first excited rotational states, because they're anisotropic, and they're coupled by long-range and tunable electric dipole-dipole interactions, which is similar to what you have in Rydberg atoms, except you don't have to excite to the Rydberg state. You have an infinite lifetime essentially of this state. So this is an advantage with respect to Rydberg states. The one disadvantage, and I should not be overselling them, is because the dipole moments tend to be limited, right? So you cannot have huge dipole moments of kilodB that typically you have with Rydberg states. So your time scales tend to be on the order of millisecond or longer for creating these interesting interactions or entangling the molecules. But I'll tell you that actually it's not so bad. So you can actually realistically use these interactions to, others have shown that you can do dipolar exchange, you can do quantum logic gates, and you can also, there's a very recent work from GILA that you can use rotational states to generate, dynamically generate a useful, metrologically useful spin squeezing, which is obviously great for measuring electric fields beyond the standard quantum limit. So another thing that ultra-cold molecules are great for is quantum simulation. I'm not going to dwell too much on this, but it's very well known. There's also actually books and chapters written about it. If you encode the spin 1/2 into the different rotational states, you're going to have, a vast array of different quantum magnetism models. Like you can encode Ising model, you can encode XXZ model, all these different flavor of XYZ models with interesting dynamics, interesting ground state, interesting equilibrium state. So that's one thing. And one advantage with respect to atoms, at least ultra-cold ground state atoms, not Rydberg atoms, is that there's no need for super exchange interactions, which are typically used to entangle different ground state atoms. So you can use directly the dipolar interactions, which is actually advantageous for, again, in combination with the infinite lifetime almost of rotational states. That's a big selling point for molecules. But this is just an example of what kind of models you can have. You can have extreme tunability. So if you encode different rotational states, your qubit spin up, down will be 0, 0, spin 1, 0, spin down will be your ground rotational state, 0, 0, where 0 is the rotational quantum number and the other 0 is the projection of rotation onto external field axis. So you can have this XXZ Heisenberg model, you can have all kinds of anisotropic models, but what is interesting is that so far most of the theoretical work, like 99.9%, was focusing on rotational states. But the thing is, like, molecules is not limited to rotational states. There's like all kind of different states, like nuclear spin, electron spin. There's this fine and hyperfine and electronic and vibrational. So hasn't been studied all that much. Like so we kind of like wanted to make a first step in that direction to explore the rich complexity of molecular structure. How can we use it for quantum information purposes? And so today I'm going to focus on one question in particular: is can we leverage this rich nuclear and electron spin degrees of freedom, which is a, rich, gives the molecular structure extreme diversity, to mitigate the limitations of rotational states, because rotational states do turns out have significant limitations, such as, for example, their coherence time tend to be quite short. So their lifetime is infinite, but their coherence time, any superposition will decay. The T time is pretty limited, but people are working on it, and the current record is actually from John Doe's group, I believe, is 93 milliseconds. So dipolar interactions are always on if you encode in rotational states, kind of not super easy to switch them off because you have to transfer molecules out of these rotational states, and also requires strong AC and DC electric fields. So that's my first question: can we mitigate this interaction? And I'm going to be talking about this. And the second question is, can we control ultra-cold molecular collisions without applying external fields, which is another interesting possibility with molecules, because there's so many internal states that you can form coherent superpositions and use quantum interference, which is what quantum coherent control is all about. So first of all, on nuclear spins, right? So nuclear spins have one big plus: they have extremely long coherence time. So one would like to encode and use quantum information and stay that, and that quantum information to stay in those degrees of freedom as long as we can, right? Generally. However, for that same reason, they're interacting only weakly with external environments, right? So very hard to entangle this, right? So there are proposals to do that, but obviously, as we know from NMR quantum computing, right, like entangling and doing gates, like it takes forever pretty much because the interactions are so weak. So here, what I'm going to propose is that I'm going to show you that we can actually entangle nuclear spins using just electric dipolar interactions, which are 1,000 times stronger than nuclear interactions between nuclear spins, and therefore you can entangle them on experimentally realistic timescales, which should and I'll also tell you about the types of entanglement that we can have in these systems. So here's the idea. So instead of encoding in different rotational states with the same spin, we encode in different, let's say, KRB rotational states of different nuclear spins. So before, people encode a nuclear spin in the same with the same M is like the projection of nuclear spin onto the axis of the external field. And then, but now, instead of choosing like M equal to M prime equal to M, as did all the previous theorists and experimentalists, now we're going to just go and choose M not equal to M prime. So our effective spin 1/2 is now, different rotational states corresponding to different nuclear spin states. So this is kind of a weird choice, and you may wonder, why would you even do that? Because if we polarize spins with nuclear spins with external magnetic field, right, the electric dipole interaction is diagonal in the nuclear spin degree of freedom. It's electric interaction. Nuclear spins respond to magnetic fields. So they don't really talk to each other all that much. But it turns out in molecules, there's this weirdness that's called actual transition, the expectation value of the, of the dipole, and I'm going to go back, and it doesn't go back for some reason. Yeah, it goes forward, and you already know all of my slides. so sorry about that. It just keeps going. So how do I go back? Like there's a back button. Okay, great. So I'm just gonna scroll very fast so that you don't have a chance. So anyway, the expectation values of electric dipole moment are different. Like, because we have chosen two different rotational states to represent a qubit, right? Like here, like one is n equal to 0, non-rotating, the other is n equal to 1. The dipole moments, the expectation values of electric dipole moments in these different nuclear spin rotational states is different. And they're different because they're rotating differently, and they're responding to external electric, they're generating, in other words, the electric fields differently at the point where the other molecule is, right? So because it's rotating differently, the electric field at the point of the other molecule will be different. And because of that, this dipole moment is different, and the dipole interaction will be different. And this is kind of the key to engineering entanglement, because if those dipoles were exactly the same, there wouldn't be any interactions. Yes, question. Rotational states, yes. 0 tilde means rotational state in the presence of external field, and hence the tilde, because different rotational states are coupled, but we're still using the rotational states. Because there's no crossing, we can label them as still birotational indices. The nuclear is M. M is the projection of nuclear spin onto external magnetic field axis. Yes, so these different dipole moments are the key. And another key is that the off-diagonal element of the dipole moment, of the electric dipole moment in the basis of this qubit basis is 0. That's because, again, the dipole moment is just electric dipole moment, and different M states, they're diagonal. They don't talk they correspond to different nuclear spin projections, and therefore this off-diagonal element is 0. And this is a feature of this encoding that enables we can actually encode the dipolar interaction now, since we know the matrix elements of the dipole moment, right? We can actually write down right away the interaction between the two qubits, right? Because it's just the dipolar interaction which is on top of that. Like we can see that there is this. If we know the matrix elements of these individual dipoles, we can actually immediately write down the matrix in the 2-qubit basis, right? And the 2-qubit basis, this is actually quite an interesting matrix, because there's a lot of zeros, but the effective two-body, we can write down the effective two-body spin-spin interaction in this way, and it will have generally this, J-perp. It will just as a form of a spin model with the Ising term and the this perpendicular transverse spin coupling term. And the spin coupling term is actually proportional. The perp part is proportional to the off-diagonal dipole matrix element, and the Ising term is proportional to the difference between the different expectation values of the electric dipole moment. So this is kind of a general result. It is completely general. In our particular case, because we have no off-diagonal element of the electric dipole interaction, because we're using different nuclear spin states, what we end up with is this term is going to be non-zero, but this term is going to be 0. So we actually engineer the Ising model. So we just engineer a quantum Ising model with this kind of qubit encoding, right? So and the constants in the Ising model, they actually depending on the angles, of course. Between the theta is the angle between the orientation of the molecule and the axis that joins the molecules, and capital Rij is the difference between two molecules. Typically in an optical lattice, for example, setup, we want to put a molecule in, it's about 500 nanometers. Can be slightly smaller, but not too much smaller. So so therefore we have actually shown that it's a simple long-range dipolar Ising model, and it's great because we know that Ising model is a key to with it we can generate some useful quantum states, like for example cluster states, right? We know that if we have short-range Ising model, we can generate things like cluster states, and if you haven't seen cluster states, just a very short introduction, it's just highly entangled states with localized entanglement. So the entanglement is is site dependent, and it's actually a particular subset of a graph, so-called graph states. So the two-qubit cluster state is essentially a Bell state, is a locally like LOCC equivalent to a Bell state. 3-qubit can be LOCC equivalent to a GHD state, but 4-qubit cluster state is different, is not a GHD state. So it's a more complicated state, but the point is that you can implement them, you can use them for one-way quantum computing, as we know, and by measuring them, you can actually prepare all different kinds of entangled states that are interesting. So that's why we actually can now use molecules to prepare some useful cluster states and to do one-way quantum computing with them. There's a caveat, which is a long-range part of a cluster state. So it's the real cluster state relies on short-range interactions, but yeah, we have long-range interactions, but actually we have a proxy cluster state, which has long-range character, which is actually quite useful, as I'll show you later. in this talk. So here's a protocol we actually came up with for generating this long-lived cluster states, because remember, they're nuclear spin states, so they're going to be much more long-lived, much more interesting or experimentally relevant than the one that people try to create with rotational states. So so first we initialize, we have an optical lattice of molecules, okay, that's a prerequisite. And then we start our protocol, right? So we begin with the different nuclear spin states in the ground rotational states. So because the dipoles are the same, they're not interacting. So this is like non-interacting ensemble of molecules. So to induce to start them evolution under long-range Ising Hamiltonian, we prepare them in a spin rotational superposition. So we excite one of the molecules into the rotational excited state with a different nuclear spin. And once they're in this superposition, right, because these two states are coupled by the Ising type of interaction, so they're going to evolve into a cluster state after a certain time, which is known as a cluster's time. It's actually inversely proportional to the Ising coupling constant, which is inversely, in other words, inversely proportional to the square of the dipole moment. So the longer the dipole moment, the larger the dipole moment is, the shorter the time scale. So that's the advantage of working with molecules with larger dipole moments, such as sodium, lithium, cesium has about 65, I believe. So this is KRB scale, the time scale. So all the results I'll show you is for the classic KRB molecule that was first created at ultra-low temperatures at Gila. So it's quite feasible already for KRB molecules. So then we evolve, right? And then after the evolution is done, we have to actually transfer them back from this rotational excited nuclear spin superposition to the rotational ground superposition of the different nuclear spin states. And then we obtain long-lived cluster states involving nuclear spins, which we can store, and then we can do measurements on that final state in order to implement protocols of one-way quantum computing. So that's kind of how one can go about this. So this is just some detailed application to KRB, in particular with all the numbers adapted to KRB. So this is a ground state rotational levels with two different nuclear spin states. We start here in this blue circle, creating superposition. Then we show that we can actually excite a reasonable rotational nuclear spin superposition without exciting the other. So there's some satellite transitions. We can avoid them realistically. And so this is the Ising coupling constant as a function of external electric field. We see that it reaches a value of about 40 kilohertz. So the cluster time we can be hopeful about, we can hope for is about 16 milliseconds. So we only have to evolve at about 16 milliseconds to reach a fully entangled cluster state. So typical coherence times, that's a challenge because these states are still in this different rotational states. So we have to be sure that no detrimental effects occur during the first 16 milliseconds, or no significant decoherence occurs within this. But again, the advantage of this protocol is that the decoherence can only be detrimental or kill us during the build-up of correlations in the many-body cluster state. But after this is done, we're immediately transferring it into different nuclear spin states and we store it. Whereas normal, classical protocols, they always stay in the different rotational states, and because of that, they always subject to this detrimental, always beating the system. Whereas in this case, we limit the time scale of decoherence to physically, the creation of entanglement that we have to create it. So, and then it will be transferred out. Okay, so now I have shown you how to engineer a long-range Ising model, but it's actually not obviously with molecules, right? You can expect more, right? Because there's so much in there, so you can so many levels. And this is the Hamiltonian I showed you before, and you see that this J-perp term. J-perp term is also very interesting, right? Because if you can control this J-perp term, you can actually create so-called spin squeeze states, especially if this model, that this is the long-range interactions, right? Because this J-perp is extending over a long time, so next nearest neighbor, next nearest neighbor. Because of that, the dynamics of this many-body quantum system with long-range interaction, right, is close to kind of collective limit, right? So you can define the total spin, right, and you can think about one-axis twisting Hamiltonian, right? And actually, it was demonstrated that the dynamics in the even in the lattice and also in the bulk can be closely approximated by a one-axis twisting Hamiltonian if you have this J-perp term, which is actually quite, similar in magnitude to J, which you can kind of see if you define a collective spin, S is equal to all the S sub I, right? And then S sub I, S sub J. So this is kind of what it is, right? If the constants are the same, it's almost like one axis twisting if the interaction is uniform, right? If you can take out this 1 over R cube out of this. But it's not really, and you cannot solve it analytically because there's all this operators. Actually, Ising model can solve analytically, even the dynamics. it's kind of like expressions are very nasty, like, and especially for higher order correlations, but you can do it. But for this, like, good luck with that. So numerical simulations is our only resort. But actually, there have been done in the group of Anna Maria Ray at Gila. They did numerical simulations using truncated Wigner approximation that they developed for this dynamical quantum evolution purposes. And they have shown that you can get about 20 decibels or more of squeezing with about 4,000 molecules, as far as I remember. So really significant metrological, gain can be obtained with this evolution. So anyway, but before, like I was telling you about this, all these advantages of the XXZ model and the O1 axis twisting, right? But we need to make these off-diagonal elements non-zero in order to make that happen, right? Because otherwise, in our system, all different spins don't talk to each other. How do we do that? And then again, this weird molecular structure comes to our rescue, right? And there's a thing that's called avoided level crossing, and I was working on it when I was a postdoc here, actually in Canada, but on the east or the west coast of Canada. And turns out, actually, if you can, like, this is an n equal to 0 ground rotational state. This is n equal to 1 excited state. So you can apply a strong magnetic field. And you can have different rotational states cross. You can make them nearly degenerate, which for molecules with a small rotational constant, it's not that high of a field. This is an example for yttrium oxide molecule. You have to have an electron spin on the molecule in order to make that happen, because again, nuclear spins shifts are very small, but the electron spin splittings are pretty significant to make that happen. So near these crossings, weird things happen. Pretty much these molecular interactions, like spin rotation interaction, that couple different spin states with different rotational states. And because of that, your off-diagonal dipole, electric dipole matrix elements is no longer zero because of this so-called molecular mixing or molecular perturbations. But it has to happen in this specific resonance region, where the different rotational levels of opposite parity cross. So anyway, we can make that happen, and you can do the math. It's a simple two by two math, level system, and then you can turn out, like, you break the spin symmetry essentially with this, because you couple different spin states using electric fields, which is weird, right? So that's what you can get with molecules. It's kind of like difficult to achieve with atoms because these crossings are kind of hard to engineer. But it's not impossible with atoms, but it can be done. So anyway, so if you can mix and break the spin symmetry, you can have magnetically tunable XXZ model. And near these crossings, you see the off-diagonal electric dipole element actually has a peak, has a resonance. So, and it's very weird, right? Because it's like electric dipole interaction, and you're tuning it with a magnetic field. And this is because with magnetic field tunes the energy splitting between different parity states. This is the mechanism, right? So actually has been experimentally realized already. So in a molecular beam experiment. So you see that J-perp can be made even greater than JZ, the Ising coupling. And because of that, actually, near this point where J-perp is equal to JZ, you can get very favorable spin squeezing, as shown by numerical simulations. So here, I'm just going to show you the results. It's actually in this paper, and Anna Maria Ray has another very important paper on this back in 2020 with numerical simulations. So you see that you can have spin state, but here we're using the standard clock protocols. I'm not going to go into details of those. We just prepare coherent superposition, evolve under the one-axis twisting Hamiltonian, and just measure. So, and I have to move on to my next exciting project. Well, these are my conclusions. So we can actually pretty much, if you take one thing out of this, is just if you have an optical lattice of interesting molecules, polar molecules, you can do a lot of interesting things with it. You can prepare metrologically useful quantum entangled states. That's the conclusion. So the other point I want to talk about is that, okay, well, I mean, I have used a lot of external field control in the previous slides, like microwaves and external magnetic field. Actually, we have here, like at the University of Toronto, there is a world expert, Paul Brammer, who wrote a book on quantum control of molecular processes, which in the book, he showed that if you can make different pathways in molecular systems interfere, you can actually, very much in the spirit of Young's double slit experiment, if you can create coherent superposition of a molecular state and do something useful with it, you can actually control the outcome of a photo process or a chemical reaction by using this relative phase that is controllable by changing the phases of the initial coherent superposition. So note, this is very promising with molecules, because molecules have a lot of states, and a lot of states are, available to make the superpositions. So, it's amazing how many states, and I've shown you before. So the idea is to initialize molecule in a quantum superposition state, then vary that superposition state, and then see what happens, right? So instead of colliding molecule in a single state, you just collide them in a superposition of different states. And that's kind of the idea. There's no external field involved other than just in creating this, which is the initial coherent superposition, right? You create it and then you let it live, right? You let it be. And then you collide it with something and then you see the result. Turns out if you actually do that, let's say your initial wave function is like this, so it's kind of superposition of internal states of the same energy. Let's say A1 and A2 have the same energy, and B1 and B2 are the states of, so A is a state of molecule A, let's say, and B state is molecule B, and this 0, 0 is actually just partial waves for the relative motion of the molecules. So just like L and its projection on the field axis, let's say, on the space fixed axis. So what you get is that, I mean, obviously, if you plug that into this cross-section formula, right, you get the cross-section for scattering from a superposition to a final state of two molecules A prime, B prime. You can get a coherent superposition, right, of two amplitudes, right? So T1 is a T matrix element for the first transition, T2 is matrix element for the second transition, just like here. So T1 is like this, A1 here, and T2 is like this, the second amplitude, right? And then you basically have an interference term. If you calculate that square module squared, right, you get not only T1 squared plus T2 squared, as one would expect, right, but you also get T1 star T2 plus T2 star T1, so you get a real part of the product, right? So this is the essence of coherent control of collisions. So that we have been working on for the last couple of years. So the total cross-section looks like this. This is a very important expression. It shows that, you know, if you, theta and beta, sorry, I haven't defined them, but they are really the phases, right? The phases of this coherent superposition. So theta is the population of state A1, B1, and beta is the relative phase between them. Components of the superposition. So what you get is the cross-section actually depends on the phases, right? But the phases is something that you can prepare experimentally, right? So that shows that actually the cross-section is actually a function of eta and most importantly beta, which is really the relative phase between the different components of superposition. So in this paper with Paul Brammer and our very bright postdoc Adrian de Volder, we have shown that actually you can just cancel the cross-section. So the cross-section from a superposition to a final state can be brought to zero by choosing these superposition parameters of the initial state judiciously. For example, well, you have to be careful in choosing them, but there is a possibility, actually, you can just totally cancel the process going to a final state. Of course, when you have two channels, situation is simple, right? When you don't want to cancel, you can maximize it, for example. That's when by choosing a different set of parameters for initial coherent superposition. So that implies that, I mean, okay, the condition for that, you may be thinking, oh, this is too good to be true, and it is probably true. So the hidden assumption there is that scattering has to go through two channels, right? And in reality, there's always leaks into different channels, and but however, at ultra low temperatures, these kind of leaks can often be mitigated very very actually efficiently, because a lot of the leaks are suppressed by angular momentum conservation laws. So this is an example of an application we did for oxygen-oxygen collision. So we looked at spin exchange collision. So we have two oxygen molecules, and if you haven't seen the structure of oxygen molecules, this is a simplified approximation. So there's three levels. So there's a spin one system. So there's three levels, and you know, one oxygen molecule has three Zeeman levels, and another one has three Zeeman levels, which are degenerate. So they can scatter into, for example, one molecule can do, you know, end up in spin down state, and the other can end up in spin up state. So this is kind of spin exchange or flip flop process that can happen. Very important also in ultra cold atomic collisions. We know that people use it to generate entanglement, quantum gates, and you know, spinor BECs and so on. So the entangled superpositions look like this. So we prepare basically different Zeeman levels in a coherent superposition. This is just the parity index, sorry, the inversion symmetry index, and this is the relative phase. And then now these are our control parameters, the phases of the parameters of the phase and the population of the coherent superposition. So if the superposition is initially non-entangled, so each of the molecule, right, that's the you know, easiest to prepare an experiment. So you just take one molecule and prepare it -1, 0, and the other is 0 + 1 + 1. So you just create the superposition, and then you let them collide and see what happens. And what happens is quite remarkable, actually. So you see that the cross-section for final state 0, 0, for the molecule scattering into the final state 0, 0, which is like in the middle of that, if you remember spin one system, is actually hugely tunable. You see, you can tune it from almost 0, just like as advertised analytically before. So the leak effects are pretty insignificant here, up to a very large value actually. And why is this value large? Because at ultra low temperatures the cross sections are typically very large. So there's so-called thing that's called Wigner threshold law that makes these cross sections like absolutely humongous typically and tunable. As you know, with Feshbach resonances, you can tune it from pretty much the cross section from very large, like unitarity limit, down to almost 0, right? Because you can tune the scattering length. So anyway, so you see that this is an alternative way to control ultra-cold collision processes. Remember, there's no Feshbach resonances, there's nothing. So it's just quantum interference from a properly chosen superposition, basically cancels one scattering process in for some values of the angles and interference parameters, and then it enhances it for some other choice of the interference parameters. So actually, this system we just discovered. Well, we learned that there is there's actually experimental work was published in Nature actually a few years ago that the Nerevicius group at Weizmann Institute actually they trapped oxygen molecules, and yes, okay, and though at 800 millikelvin, so this still pretty. I should comment. There's a way to go right there in terms of temperature, because at higher temperatures this leaking effects becomes more and more important. So ultra low temperatures are really important for efficient coherent control. So if you go above about 5 millikelvin, the control kind of like gets pretty bad. So it's really important to cool the system to very low temperatures to make these interference processes as efficient as possible. So we see that, this is like 800 millikelvin current experimental record. We need about 5 millikelvin, so there's about 2 orders of magnitude they have to go before they can actually potentially observe coherent control. So this is just another example of it. Like this is a control of a branching ratio. It means that molecules can scatter into 0, 0, but they can also scatter into some other state like plus minus 1. And the very important question is that, okay, we can control the cross section, but can we control the ratio of fluxes, scattering fluxes into different final states? And turns out the answer is yes. And again, so this is, you see the middle line is that without control, without any coherent superposition, you get a factor of, it's like order of unity essentially, the branching ratio. Whereas, if you just maximize your angles and pick the right angles, you can get, it's like 10 to the 8 pretty much. So, it's vast. The control is absolutely vast. So it looks like from our calculations. So we're very excited, and we now are studying, extending these results to coherent control of ultra-cold chemical reactions. Actually, we chosen this reaction of atomic lithium plus molecular sodium lithium because the group of Wolfgang Ketterle has recently observed a number of magnetic Feshbach resonances in the related system of sodium plus sodium lithium. But we don't have potential energy surfaces for sodium lithium, so we just started doing lithium plus sodium lithium because it's easier. And then we actually using the full-scale quantum dynamics calculations with the help of Brian Kendrick's group at Los Alamos. This is actually the full numerical set of states for sodium plus lithium plus sodium lithium reaction, which you can see there's like hundreds of these states, and our postdoc Masato Morita is working on this. The idea is to obtain the cross sections and to vary the relative phase between the sodium and lithium. So basically prepare both sodium and lithium in a coherent superposition in order to control the actual chemical reactions. Sounds good. So I'm almost done. So my conclusions are that, okay, great, we can coherently control the universe, hopefully. So, but there's still some work to be done. And the real work to be done is, okay, ultra-cold chemistry, as I just told you, but also scattering resonance is a very important point, because Paul Brammer has shown about a decade ago that near scattering resonances, the coherent control actually becomes almost perfect. And we haven't taken advantage of that. So we are now trying to see what we can do near, let's say, magnetic Feshbach resonance. Can we, manipulate that resonance, maybe shift it a little bit or do something useful with it, And finally, the interesting question is, like, a lot of experimentalists are worried about reaction complex formation in ultra-cold molecular collisions has actually been recently observed by Kang-Kwen's Ni group in photoexcitation. Basically, the molecules just stick it to each other and they're lost. right? And so can we control that? Can we mitigate trap loss? Can we improve, the density and other collision and the underlying collisional properties of the system? So these are my collaborators. Nothing would be possible without them. So I just want to thank Paul Brammer, Professor Jun Yi and Anna Maria Ray from GILA, and our great postdocs, Adrian DeVolder and Masato Morita, Brian Kendrick, who did quantum reactive scattering calculations, and potential energy surface calculations were done by the Temple University group. So thank you very much for your attention.